Hello everyone, welcome back to Supplementary Tutorials. Today we'll be talking about acid-base disorders. So let's proceed. So in clinical chemistry or chemical pathology, when we talk about acid, they are substances that releases hydrogen ions or hydrogen ions when they are found in solution. And in chemistry, the measure of how acidity or basicity or acidic or let's say basic a substance is determined on the pH scale. And this is no different from the clinical settings. We also make use of pH. So pH generally is the negative logarithm of hydrogen ion concentration. And in physiological terms or in chemical pathology, pH ranges from 7.35 to 7.45. So this is the normal physiological pH. When it drops from 7.35, it means the physiological condition has become acidic. It could be the body fluid compartment. When it rises above 7.45, then it means it's becoming basic. Importance of pH, we can talk about enzyme function. Some enzymes will work best at an optimum pH or a certain pH. Okay, we can also talk about muscle contraction, we can talk about nerve conduction, etc. So pH plays an important role. When the body fluid compartment is so much acidic, it will alter some of the normal functions of the body. And when it is too basic to some part of the body or some chemicals or some enzymes will not be able to function well. Right? Now, the body must find a way to balance this acid and base that is found in the body. And this is a homeostatic mechanism. You see, the body try as much as possible to make sure that there is an equilibrium. That is what we call homeostasis. So the body has to ensure that there is no too much acid within the fluid compartment and there is no too much base. So the body has an automated way of regulating that acid and the base. So we're going to talk about acid-base homeostasis. The first thing we have is the buffering. So this is the first line of defense. Then we have the respiratory homeostasis, and then we have the renal homeostasis. So we are going to go through these three acid-base regulatory mechanisms. Alright. So let's start with the buffering. So in the buffering we have the phosphate buffering system or the phosphate buffers. We have the hydrogen carbonate or the carbonic acid buffers. Then we have the haemoglobin. Then we have proteins such as albumin. We are going to go through each one of them and see how they perform or they play a role in the buffering system. So let's start with the hydrogen carbonate. So mostly the hydrogen carbonate is found within the extracellular compartment. So let me just write this reaction here. So this is what actually happens when there is influx of hydrogen ion in the extracellular fluid compartment, or when there is excess hydrogen ion in the extracellular compartment, or when there is low pH in the extracellular compartment. The excess hydrogen binds to the hydrogen carbonates to form carbonic acid. And carbonic acid is so unstable that it dissociates into what? Carbon dioxide and then water. The carbon dioxide is then exhaled out, whilst the water remains in the extracellular fluid compartment. So this is a way to mop up all the what? The hydrogen ion. So we realize at the end of the reaction, there is no hydrogen ion produced. Therefore, it reduces or limits what? The hydrogen ion concentration. So this is what actually occurs. So therefore, this one is serving as what? As a buffer. Okay. Now let's talk about the phosphate buffers. The phosphate buffers. Okay, so this is what also happens in this reaction. When there is hydrogen influx within the intracellular fluid, what you have to take note of is that this one is found in the intracellular. This one's intracellular. So when there is so much hydrogen ion concentration within the intracellular fluid, what happens is that the hydrogen ion binds to the hydrogen phosphate to form dihydrogen phosphate. So this is also a way of mopping up excess hydrogen ions in the intracellular compartment. Right. Okay. Now let's talk about how the hemoglobin can act as a buffering system. So the hemoglobin in its deoxygenated state, that is deoxyhemoglobin, has a high affinity to hydrogen ions. So hemoglobin in its deoxygenated state binds to hydrogen ion to form something like HHB kind of thing. So this one is a hemoglobin that has hydrogen ion attached to it. So this is also a way of what? Mopping up the hydrogen ions from the intravascular compartment. Okay. And then moreover, there is something we call the Bohr effect. Bohr effect. When the hemoglobin that has the hydrogen ion binding to it is found circulating within the bloodstream, it gives the hemoglobin a high affinity for oxygen, and it allows more oxygen to be what? To be attracted to this one. And this is also a way of reducing the amount of hydrogen ions. So this is what we call the Bohr effect. So the Bohr effect is also one way hemoglobin can act as a buffer. So once the hydrogen ion is attached to the hemoglobin, it increases its affinity for what? For oxygen. Alright. Now let's talk about how protein can act as a buffer. So we know that the most abundant protein that we have, or among the plasma protein, is albumin. So albumin has the ability to bind to large molecules that are both acidic and basic. So in a way, albumin also helps us in acid-base regulation. So albumin is one of the proteins that helps in acid-base regulation. Besides, there are other plasma proteins that are also responsible for what? Acid-base regulation. So that is under the buffering system. Now let's talk about the respiratory system. So the respiratory system has a way of regulating acid and then base. So there are two things involved. Either there is an elimination of carbon dioxide or there is a retention of carbon dioxide, and this is a reverse reaction. So therefore, equilibrium position must definitely shift to one way end. Okay, so for instance, when there is so much carbon dioxide, but let's see what happens when there is so much carbon dioxide in the body. So how does the respiratory system enhances acid-base buffering? Okay, so it's just a simple mechanism. So when there is so much carbon dioxide within the body, or when there is carbon dioxide retention, this is what actually happens. When there is carbon dioxide retention, this is what actually happens in the body. So carbon dioxide combines with water to form bicarbonate, which will dissociate to form hydrogen ions and hydrogen carbonate. Hydrogen ions and hydrogen carbonate. Okay, so when there is so much carbon dioxide in the body, it leads to the production of excess of hydrogen ions, and this one will cause more acidity. This one will cause more acidity and reduce the pH. So the body has a compensatory mechanism, and that compensatory mechanism is the increase of breath, something we call hyperventilation. So when the person keeps breathing rapidly, it means the person is what? Reducing the amount of carbon dioxide, CO2 is reduced in the compensatory mechanism. And when that happens, the equilibrium position shifts to the left hand side. So you realize that the reaction will no more go forward, it will rather be reversed. And once there is reverse reaction, it means the amount of hydrogen ion here will be reduced. And once the hydrogen ion reduces, pH increases to compensate for this. So that is how the respiratory system also does the buffering. Okay, so once there is excess carbon dioxide in the body, carbon dioxide will react with water to form hydrogen carbonate. person begins to what? Hyperventilate, breathe rapidly, to get rid of the excess carbon dioxide. And when that happens, equilibrium position shifts to the left hand side. And once the equilibrium position shifts to the left hand side, it means the number of hydrogen ion production will reduce, and therefore the pH will also rise. So that is how come the respiratory system also contributes to buffering. Now let's talk about the renal system. In the renal system, we have excretion of hydrogen ions, generation of hydrogen carbonate ion, then reabsorption of hydrogen carbonate ion. And of course, we know what will happen when there is excretion of hydrogen ion. So when there is excretion of hydrogen ion, it means we are getting rid of what? The hydrogen ions. Therefore, the pH will increase. And when there is generation of hydrogen carbonate ions too, it is also going to lead to what? To an increase in pH. And there is reabsorption of hydrogen carbonate. Is going to be what? A decrease in the pH. Alright. Now let's talk about the acid-base disorders. The acid-base disorders. So in the acid-base disorders, we have two major disorders. We have the acidosis and the alkalosis. So, and acidosis, we have metabolic acidosis and respiratory acidosis. And the alkalosis, we have metabolic alkalosis and respiratory alkalosis. So how do we determine if the condition is an acidic condition or a basic condition? Less to know for us to know that this is a metabolic condition or respiratory condition. So in situations like this, we have parameters that we measure in the laboratory. We have the partial pressure of carbon dioxide. We even have the partial pressure of oxygen. That's oxygen saturation. We also have the bicarbonate too. Okay, and then we measure the pH. Now take note of this. Take notice of this one. Whenever you see pH, it determines whether the condition is acidic or basic. So any moment the pH reduces, you have to put it in your head that it's got something to do with what? Acidosis. Anytime the pH is increased, it's got something to do with what? Alkalosis. Now, how would you know whether it's respiratory or metabolic? Now I'm going to use the partial pressure of carbon dioxide. So once the carbon dioxide increases, you have to know that this is what? It is a respiratory condition. Once it's got to do with carbon dioxide, it's a respiratory condition. And once it's got to do with hydrogen carbonate, it's a metabolic condition. So that is how we are going to use to distinguish between respiratory acidosis or respiratory what? Alkalosis, or respiratory alkalosis or metabolic what? Alkalosis. Okay, so now let's talk about metabolic acidosis. So when we say acidosis, we are talking about an increase in what? Hydrogen ion concentration or acid in the body, and a lowering of the pH. So once you see acidosis, the first thing that has to come to your mind is that the pH must reduce. So you look out for parameters that have their pH reduced, so you know that it's acidosis. Now, how would you know whether it's metabolic or respiratory? So let's check the parameters for the metabolic. So we have the hydrogen carbonate here being reduced. We have the hydrogen ions being increased, and then the pH being reduced. Okay. So this is what actually happens when it's metabolic acidosis. The hydrogen carbonate here reduces. So just presume that the hydrogen carbonate here is what is basic. So there's a reduction here, and then there's an increase in hydrogen ion concentration. And once there's an increase in hydrogen ion concentration, definitely there is going to be what? is respiratory, the partial pressure for carbon dioxide will increase. Once there is excess carbon dioxide, you know that it leads to excess acidity. And there is carbon dioxide retention too. So once there is carbon dioxide, there is carbon dioxide retention, and there is a drop in pH. So that's how you're going to know whether it's respiratory what? Acidosis. Now, how are we going to know whether it's when it's alkalosis? When it's alkalosis, the pH increases. That's what we have to put in your head. Whether it's respiratory or metabolic, the pH must increase. The pH must increase. And then the partial pressure of what? The pH must increase on both sides. Yeah. So how are we going to know whether it's metabolic or what? Respiratory? The same thing. Once you see that there is hydrogen carbonate, then you have to know that it's got something to do with what? Metabolism or metabolic. So once the hydrogen carbonate increases, it is what? Metabolic alkalosis. Once there's a drop in the hydrogen ion concentration, then it's metabolic. And once there's a peak, remember the hydrogen ion concentration will let you know whether the pH will peak or will come down. So when the hydrogen ion concentration goes down, the pH increases, and vice versa. Okay. Then respiratory alkalosis. In respiratory alkalosis, the partial pressure for carbon dioxide comes down. Yes. So in acidic condition, partial pressure of carbon dioxide increases. In basic or alkaline condition, partial pressure of carbon dioxide will reduce, and then CO2 is cleared from the system. Once this one is reduced, definitely CO2 is cleared from the system, and the pH rather what increases. So that is it. Now there's always a compensatory mechanism for this one. So there's a compensatory mechanism for metabolic acidosis, there's a compensatory mechanism for metabolic alkalosis, and there's a compensatory mechanism for respiratory acidosis, there's a compensatory mechanism for metabolic alkalosis, and there's also a compensatory mechanism for what? Respiratory alkalosis. In our next video, we are going to talk about the how the excretion of hydrogen carbonate can lead to any of this one, or the excretion of hydrogen ions can lead to either of these ones, or the generation of hydrogen carbonate can lead to either of this one, or the reabsorption of hydrogen carbonate can